So okay, now uh, let's see some applications. All right. Now, first is SVD can tell how close a square matrix A is to being singular. Well, let's see how. So, what this slide says is that if you take the ratio of largest singular value to the smallest singular value, sigma 1 is the largest, sigma k is the smallest. All right. If C is infinite, then A is singular. Well, let's see why is that. It's just simple matrix algebra. You see, A is this, right? Now, if you take the determinant on both sides, what do you get? You get determinant of, I hope that you know that determinant has this property that if you take determinant of a product of matrices, then it distributes in the sense that this is equal to determinant of U times determinant of this diagonal matrix times determinant of V transpose. Now, here's the important thing. Determinant of U is non-zero. Why? Because this is an orthogonal matrix. And similarly, determinant of V transpose is non-zero because again, this is an orthogonal matrix. So that means determinant of A is zero if and only if determinant of sigma is zero. All right. Now, so if this quantity is zero, then this is zero. And if this is zero, then this will be zero. Now, when is determinant of sigma going to be zero? Now, if you recall, determinant of any n cross n matrix is the product of its eigenvalues. So if at least if even if one value becomes eigenvalue becomes zero, then the determinant of that matrix becomes zero, and that is exactly what's happening here. C will be infinite when sigma k is zero. So basically, what it's saying is if the smallest eigenvalue becomes zero, all right, if the smallest eigenvalue becomes zero, then the sigma matrix will have determinant as zero, and that would imply that A has determinant zero, which by definition means that A is a singular matrix, which that means it is not invertible. Okay, that's one thing. Then, so this is a fancy application, digital signal processing. Uh, so we are not worried about the technical details of this particular application. It's just to give you an idea how SVD is used in a variety of domains. So what's happening here is you have a matrix, all right, and suppose it represents some signal, all right. It could be any signal. So it could be an electric signal or whatever, all right, or it could be an image or anything. Now, this signal might have lot of noise in it, in the sense that lot of data in that matrix might be useless for us, which is not giving us any information about the main content that you are interested in. All right. So what you do is you compute the SVD of that matrix. All right. Again, you discard the small singular values. That is, you discard the small sigma i's. All right. So you get a truncated matrix. Now it can be shown. We are not going to prove it here, but it can be shown that small singular values predominantly represent this noise. So by removing small singular values, you are just getting rid of the noisy part of the matrix. All right. And just as we saw a few minutes before, the rank K matrix that you get after truncation, that represents the filtered signal. In that in that notation, I wrote it as X tilde. So this X tilde represents the filtered signal with less noise. All right. Okay. So let's move forward. So there are a lot of applications of SVD. So data reduction and compression. Low rank approximation is what we discussed. These are something which we are going to discuss next. And I think these are clear as well. I mean, in the sense that how we are actually reducing the dimension of our data matrix, right? Okay. So, yeah. So now I would like to discuss one application which is quite common. And again, once again, I would bog you down with some maths, not so much, but a little bit. just to give you an idea how singular value decomposition is actually applied in linear algebra. Well, you see, okay, so let me go to, all right, let me go to the blank page. I hope I have one. Yeah, I have two. Good, perfect. All right. Now, recall from your linear algebra course from engineering or sciences or wherever you have done it before. You see, you have a system of linear equations which is generally written as ax equal to b. I think that this must be familiar to most of you, right? This is the standard linear system of equations where a is known, b is known, and well, the the whole task is to find out this quantity x. All right. So essentially, what this means is, does there exist a solution to this system? All right. Now, as I said before, if you're if this a is an if a is a square matrix, then our life becomes very easy. All right. Because in case a is square, we can talk about its inverse. It may or may not exist, but we can talk about its inverse. Suppose a is invertible, then x is nothing but you just multiply both sides by a inverse, and your solution is then nothing but a inverse b. Simple, you're done. In case a is not square, in case a is not invertible, then you have some other techniques to actually find out a solution, and SVD actually helps us to do that. And not only that, it helps us to find out solutions in case of non-square matrices as well. All right. Okay. Now there are two cases. One is known as something known as underdetermined system. All right. What is this underdetermined system? Well, in this case, in principle, you have more number of you have uh, more number of equations and less number of variables. All right. So if you expand this, you get a linear system in which the variables are less, whereas the number of equations they solve is more. All right. In that case, in general, there is no solution. In general, there is no solution, in the sense that if you take an arbitrary system in which you have uh, you have lot of equations but very less number of variables, then it's highly probable that you won't get any solution to that system, right? Right. You can imagine it like this: you have this matrix A, you have this vector x. Now this vector x is actually small in the sense that there are not so many degrees of freedom to actually cover these equations. You can think of it like that. All right. Okay. How does SVD help us to solve this system? Well, you see, since A is an n cross m matrix, and suppose n is not square, n is not equal to m, now you can't invert it directly. All right. What you do is you take the singular value decomposition of A. All right. So you write A as this. All right. Now, one fact that I'm going to use is an orthogonal matrix is invertible. See, this is an n cross n matrix. This is n cross m, and this is m cross m. And u and v both are invertible. All right. So now what I have to do is I just have to multiply both sides by u inverse, or you can equivalently multiply it by u transpose, because you see u transpose u is equal to u transpose equal to I. So the inverse of u is nothing but u transpose. All right, it follows from this equation. All right. Now when you multiply it by u transpose, you get u transpose b equal to u sigma v transpose x. And this is nothing but the identity. All right. Similarly, Now, since sigma is an n cross m matrix, you can't take its inverse. But what's important is if you multiply it by the, since it is a diagonal matrix, right? Remember, it's a diagonal matrix. So if you multiply it by a matrix which has its non, see, the diagonal entries of sigma are sigma 1, sigma 2, and so on. All right. Now, what you do is sigma inverse you take as reciprocal of these values, of the non-zero values. All right. And you just take that as sigma inverse and you multiply it with this. All right. And again, you get the identity matrix. And similarly, then you multiply again by V. So what you get is X is equal to, you would get V sigma inverse U transpose D. And this quantity here, this is denoted by X dagger. This is known as the Moore-Penrose inverse. Right? Now, this is not an exact solution. See, in case of underdetermined system, I told you that this system might not have any solution. But this solution that we have got is closest to a possible solution. This is as close to, this is in some sense a best fit. All right, this is the best fit solution in this following sense, that this X, suppose I called it as X subscript S, this X has the minimum Frobenius norm. All right, this Frobenius norm is something which we defined earlier. This is nothing but the summation of, if xs is, let's say, x1 till xn, then x norm of xs is nothing but summation mod xi square I equal to 1 to n. Just this, you take the square of every entry and you add them all up. All right. So this is a best fit solution such that this norm is minimum. So of all the possible values that you take of xs, this particular value, which is given by this formula, actually gives you the minimum Frobenius norm. All right. So you won't get an exact solution, but you get an approximate one. All right. And it is best in this sense that it has the minimum Frobenius norm. On the other hand, you might have an overdetermined system. All right. You might have an overdetermined system. What is this overdetermined system? Well, it's just the opposite of an underdetermined system. Now you have more variables and less equations, lesser equations. All right. Now, from theory of linear algebra, it turns out that in general, this system, which has, this is n cross m, this is n cross 1, this is n cross 1 vector. So, overdetermined system is one where n is greater than n. So, in general, this has infinitely many solutions, right? Now, our task is to find the best one. There will be infinite, in general, there will be infinitely many vectors x which will satisfy this system of equations. And my task is to find out the best one. Now, best in what sense? Again, you have this x tilde, just like the previous case, you have this, right? This is your x dagger, which is the pseudo inverse or the Moore-Penrose inverse. Now you see, this is best in the following sense. This solution, this particular solution, this gives you the minimum Frobenius norm in the following sense. If you take this quantity, all right. Now, if you consider this quantity and you take the Frobenius norm, then this will actually give you the minimum value, this solution. All right. This solution will actually give you the minimum value of the Frobenius norm in this sense. So this is the best fit in terms of Frobenius norm and the minimization problem. This is the best fit in this sense. All right. So yeah. So that's about it. So this was a little math intensive. Well, sorry about that, but it was essential as far as I'm concerned. So let's see. All right, so we've already covered this, and yeah. So another application of singular value decomposition is, uh, is an image compression. So as I mentioned earlier, just applying SVD on an image will not compress it. It's not enough that you take the data matrix and you write it as U sigma V transpose and you say you are done. No, there is nothing extra or special that you have done till now. What's important is you must retain the first singular values, first few singular values that contain maximum image information. All right. And you must discard the remaining values that contain negligible information. All right. So this is in general how you do SVD. Okay. Now this is now the question is, how do you actually compute the SVD? Right. This is a natural question. Well, there are a lot of ways. There are a lot of ways to actually compute the SVD, but the most intuitive way to understand that what SVD is and to see how it is calculated is using something known as the correlation matrix. All right. So essentially, what we do is, see, I don't know if we have enough time left. Uh, let me see. Okay. Now see, I'll just give you an idea about what's happening here. What's happening is you take an input matrix A, you calculate A transpose and A transpose A. All right. Now there are some special features of these matrices. One is that these two matrices are symmetric. All right. These are symmetric matrices. All right. Which implies that the eigenvalues are real. Now this is something which needs to be proved. I'm not going to prove it now, but you can take it as a fact. If you believe this, then symmetric matrices, real symmetric matrices, have eigenvalues which are real. All right. And not only this, AA transpose and A transpose A are positive definite, positive semi-definite. All right. These are positive semi-definite matrices. This again, you take this as a fact. And since they are positive semi-definite, this implies all the eigenvalues are actually greater than equal to 0. So combining these two facts, what we have is that AA transpose and A transpose A have real eigenvalues which are real numbers, not complex numbers, purely real numbers, and they are greater than equal to 0. All right, that is one thing. This is some prop. These are some standard properties of these matrices. Okay. Now what you do is you calculate these two quantities. Well, what you do is you substitute A is equal to U sigma V transpose. You substitute it here. All right. So what we get is, we will get, for example, if I take A transpose, then I'll get A transpose equal to some expression. All right. The important thing is these the left the vectors, the column vectors of U, they are known as, the standard terminology is, they're known as left singular vectors, right? Left singular vectors. And the reason for that is these columns are actually the eigenvectors of the matrix AA transpose and A transpose A. So the columns of U and V transpose, they're actually the eigenvectors of these two matrices, corresponding to the eigenvalues, which are actually sigma 1 square, sigma 2 square, and so on. All right. I'm not going to do the computation here because I think that I've already done a lot of maths already. So I don't want to bog you down with more details. But essentially, what's happening is, you see, this is what these two statements say. All right. The columns of U are actually the eigenvectors corresponding to the eigenvalues of A transpose. Similarly, columns of V are the eigenvectors of A transpose A. All right. Okay. So that's one thing. Now, usually we don't use A transpose and A transpose A to compute the SVD of a matrix. This is not how we proceed. For the simple reason, A transpose and A transpose A, they are huge matrices. And it's very computationally inefficient to solve this system of equations to find the U and V. All right. We have better ways to compute U, V, and sigma. For example, QR decomposition and a lot of other algorithms. But this is the most intuitive way to understand what's going on actually. But it's not the most efficient way. All right. Okay. This is what I mentioned just now. Uh, now, this is just an application of SVD in image compression. So why do we need compression? Well, for the obvious reasons, we want to store data efficiently, we want to transmit it faster, and we want to save memory, bandwidth, and cost. So these are quite obvious reasons why we need compression. And okay, so again, you see, this point says that while performing the SVD compression, the sum is not performed to the very last singular value. Well, what this means is, if you remember, I wrote down X as something like this. And suppose I truncate it at this point. And I ignore all the other things. All right. So what this is saying, we don't perform the SVD, we don't perform it to the very last singular value. That is, essentially what it's saying is, we have to remove some of the singular values. All right, small enough values are dropped. The closest rank k is acquired by truncating those sums after the first k terms. Well, here k is nothing but r. So you take the first r terms. This gives you a rank r approximation. And then we have already discussed all these things. The digital image corresponding to the truncated matrix will still have very close resemblance to the original image. All right. So we have already seen all this in action. Lowest rank k approximation, again, we have seen what this is. Now, this is actually sigma. All right. So the basic idea of lowest rank k approximation is we approximate the matrix A by adding only the first few terms of the series. All right. We have seen this already. Now, here is the important point. As k increases, that is, the more number of terms you take, the image quality increases. It is closer to the actual image, but the amount of memory needed to store the image, that also increases. All right. This means smaller ranked SVD approximations are preferable, and this brings us to the very important question: how do you choose your k? All right, and that's an entirely different thing. There are a lot of algorithms, and there are a lot of technicalities involved, but that's not important for us. That's specific to the problem at hand, and you can actually learn them on the go. But the most important point here of this webinar is to understand the basic concepts of SVD and what actually is this thing. All right. This is an example. So when you take k is equal to 2, that is, you just take a rank 2 matrix to approximate your original matrix, you get a very blurry image. As you increase your k, you get better and better quality image. But of course, the amount of memory needed to store the image will increase. All right, so you are looking for an optimal kind of thing. So you see, an optimization problem already enters into the picture. All right, so you are not only working with linear algebra, you have an optimization problem as well. All right. Anyways, that was just a side remark. All right. So these are some summary of what we have done till now. See, k actually represents the number of eigenvalues that we have used. See, when we take till sigma k, so we have actually taken k eigenvalues, right? That is what it is saying, nothing else. All right. And smaller the value of k, greater is the compression ratio. Well, that essentially means that you will take lesser memory to store the image, and obviously the compression ratio will be high, but the image quality decreases. All right. And if K increases, then the image quality improves, but again, the storage space required will be more. And when K is equal to the rank of the image matrix, then the reconstructed image is nearly same as the original one. All right. So this is a fact, or you can take it as an observation. All right. Okay. So as I mentioned earlier, the most important singular value, that is sigma 1 is greater than equal to sigma 2 and so on. The first one is most important. They produce the most important unit eigenvectors. That is, corresponding to this, u1 and v1 are the most important vectors. Then u2 and v2 are second most important, and so on. All right. Okay. So by now you must have guessed, you must have observed that essentially we are arranging our matrix in the order of importance. All right. So that is in some sense the fundamental concept uh, of SVD. All right. Okay. Again, we can eliminate huge portions of our matrix without losing quality. What this means is we are actually removing redundant data or singular values which are negligibly small. And then again, the problem of choosing an optimum value of K with an acceptable error, of course, and we need it in such a way that it conveys most of the information present in the original image and also has an acceptable file size. So we have already discussed all this.